let's look at the second example here. If mn is even, then m is even or n is even for all integer values of mn, and we need to use the contrapositive to prove this. So in terms of our original statement, what they're asking us to prove is that if mn is even, then m is even or n is even for all values of mn that are integers. Okay, so our P then Q statement, our P implies Q statement says mn is even, and that implies that m is even or n is even for all integer values of m and n. Our contrapositive, remember we're going to swap our P and our Q and negate both of them. So here our requirement to prove says that if m is odd or n is odd, sorry, not or, and remember when we're negating an or statement over here, it becomes an and. So and n is odd, then mn is odd for all integer values of m and n. So our not Q implying not P is m is odd and n is odd implies that mn is odd for all values of m and n that are integers. All right, so the first thing we're going to need to do is to let m and n be integers and odd. So here's our proof. So we're going to let m and n be integers and m and n are odd. Now in order to make odd integers, I have to multiply them by 2 and add 1. So we're going to let m equal some variable times 2 plus 1, where k is some integer, and n will make a different variable, so 2p plus 1, and p is also some integer. All right, so I've now defined those two, and I need to show that m times n is odd. So m times n is just going to be 2k plus 1 times 2p plus 1, and that becomes 4kp plus 2k plus 2p plus 1. And hopefully you realize, start looking for these patterns, and you can see that each one of these can be divided by 2. So I can take out a common factor of 2, and that leaves me 2kp plus k plus p, and I'm very strategically keeping my plus 1 over there, because this then, if I can turn 2kp plus k plus p into some other variable, which is another integer, because when I'm multiplying or adding, subtracting integers, I get another integer. So I'm going to say here 2kp plus k plus p is an integer, and I'm going to let 2kp plus k plus p equal t. And it doesn't really matter what I call it, because t is also an integer. And that then gives me that mn is equal to 2t plus 1. And remember, we've said that if you multiply anything by 2, it's even, and if I add 1, it is odd. So therefore, mn is odd, and therefore the contrapositive statement is true. So therefore, if mn is even, that implies that m or n is even for all values of mn that are integers.